the previous module, I talked about the ladder operator in angular momentum, and I showed you that the commutator relationships of the ladder operator, and I also talked about the eigenvalues of the raising and lowering operator with respect to both LZ operator and L square operator. I said you that when you operate with L plus or raising operator on LZ eigenvalue equation, the eigenvalue increases. If you operate with L minus on the eigenvalue equation of LZ, eigenvalue decreases. But if you operate with L plus on L square, phi is equal to C phi eigenvalue equation, then you don't find that the eigenvalue decreases or increases. Now, if we go for a relationship between the eigenvalue of L square and LZ, what do we get? This is known to you that when you operate with LZ on a function, what you get is this equation: mk phi k, where k is equal to 0, 1, 2, 3, and mk is equal to m plus minus k h cross, where phi k is equal to L plus minus k. Okay. So, if you write this equation, L square phi k, then you get C only, C phi k, where phi k is equal to L plus minus k, phi is equal to k is equal to 0, 1, 2, 3. The eigenvalue obtained for LZ can't be infinite. So, what does it mean? It means that if you keep on using the ladder operator time and again, then you will keep on getting the higher value and higher value and higher value always. No, it is not so. Okay. So, LZ can't be infinite and must be bounded. Okay. The ladder cannot extend indefinitely. So, continuing with this ladder operator, operating again with LZ on the first equation, LZ phi k is equal to mk phi k, what do you get? So, LZ square phi k is equal to LZ, operating again with LZ. We are not operating here with L plus. So, operating LZ twice on this equation will give you LZ mk phi k. So, it will be mk LZ phi k, also we can write mk square into phi k. Subtracting equation 3 from equation 2 will give you what? If you subtract this equation, then on the left hand side you will have L square minus LZ square multiplied by phi k. So, on the left hand side you have L square phi k minus LZ square phi k, and on the right hand side you will have C phi k minus mk square phi k. No issue. Okay. And then if you rearrange this, you arrange it like this one. L square is actually what? This you can write as L square minus LZ square into phi k. And what is L square? L square is Lx square plus Ly square plus Lz square. Okay. So, L square minus Lz square will be equal to Lx square plus Ly square. So, that is why it is L square minus Lz square I have written as Lx square plus Ly square and phi k. By definition, L square is Lx square plus Ly square plus Lz square. In the first few, I think first or second module, I gave you the definition. Okay. So, if you subtract this one, equation 3 from equation 2, what you get is C minus mk square here, and this you get as Lx square plus Ly square. Okay. Now, you see, what is the significance of this relationship is that the operator Lx square plus Ly square is a non-negative term, because it is sum of the squared of the variables. So, if it is a non-negative term, then you should get on the right hand side eigenvalue also a positive term. And for this equation C minus mk square to be positive, C must be greater than or equal to mk square. So, what do you get? C must be greater than or equal to mk square, or C raised to the power 1 by 2 must be greater than mk, where k is equal to what? How many times you are operating. So, it could be 0, 1, 2, 3 and so on. Okay. So, this is the limitation of k, that k is decided by the value of C. Okay. it must be less than the C. And if K is limited, then number of times you can operate on a particular eigenvalue equation it gets limited, and so the LZ can't be infinite, it becomes finite. Okay, so that's what is the relationship between eigenvalues of L square and LZ. Mk is the eigenvalue of LZ and C is the eigenvalue of L square. So the relation between these two eigenvalues of L square and LZ is that C is greater than or equal to Mk square, and this you obtain from simple relationship, simple eigenfunction relationship, nothing else. On LZ eigenvalue equation, I operated again with LZ and then I subtracted. That's all. Okay. So the relationship between eigenvalue and L square LZ is eigenvalue of L square is C, which is always greater than or equal to the eigenvalue of LZ, that is Mk square. Okay. So now if I go with this also, it's the same thing, but let's look at this one. That suppose we get the LZ, if you remember, if you operate with LZ on a phi function, what you get is this we talked about mh cross phi. So remember this equation and look at this equation. If we suppose phi to be maximum, then the m also should be maximum. Okay, h cross is omitted because h cross is the atomic unit. Okay, so h cross we can omit h cross, and then you can, in the atomic unit you can write LZ phi is equal to m phi, where m is the, if you remember, I talked about in the phi equation solution the significance of the phi eigenfunction, that m gives you the magnetic quantum number. So anyway, so that same I am writing m max and m min. Okay, for maximum value and for minimum value of the LZ eigenvalue. Then operate by L plus on LZ phi max. What do you get? Means it's already maximum, and again you want to operate with L plus a raising operator. So the value should be raised, the value should be higher, and let's see what happens. If you operate this one, if you operate with this one, what do you get? L plus is LZ L plus minus h cross L plus phi max, and then L plus m max into phi max. This you can write. And if you, it's L plus LZ, and L plus LZ means what? Is equal to this one. This was the equation which we derived earlier, L plus LZ. So you get this one, and if you take the LZ outside, then you have L plus phi max, and bring this part on the right hand side. So it becomes m max plus h cross L plus phi max. So L plus phi max is now the eigenfunction. L plus phi max is now the eigenfunction, and the eigenvalue of now LZ operator is m max plus h cross. Okay, I am using this relationship. L plus LZ is equal to this one. L plus LZ is LZ L plus minus h cross L. This we already did. So from this you get this one. Now here we obtain an eigenvalue m max plus h cross, but we suppose it to be maximum value of the eigenvalue. So it's a contradiction, as we define the maximum eigenvalue is m max for LZ operator. Now what will happen? So the only way out is that L plus phi max is equal to 0. Okay. So if you put operating on L plus phi max is equal to, in order to get rid of this contradiction, you say that L plus phi max is equal to 0. Now if L plus phi max is equal to 0, then operating on L plus phi max by 0, L plus phi max is equal to 0 by L minus. Here we operated with L plus, now I am operating with L minus on this function. And what do we get? So L minus L plus phi max is equal to 0. So L minus is equal to Lx minus ILy, and L plus is equal to Lx plus ILy into 5x is equal to 0. And if you open it up, Lx square plus Ly square minus ILy Lx plus ILy Lx Ly, 5x is equal to 0. And if you rearrange, then L square minus Lz square. This I can write. I have just written Lx square. L square is, this you can write because L square, L square is equal to Lx square plus Ly square plus Lz square. These are basic definitions. Okay. So Lx square plus Ly square will be L square minus Lz square. So this part you can write it like this one, and then you can take I as common, and it will be Lx Ly minus Ly Lx into 5x equal to 0. So this will be what? This will be commutator of, this you write commutator of Lx Ly and L square minus Lz square, and this will be commutator will be IH cross Lz. Okay. So I square will become minus, and you have L square minus Lz square minus H cross Lz, 5x is equal to 0. Okay. This commutator relationship we did in the previous module. Okay, previous to previous module perhaps. So all this module we proved that relationship. Now Lz phi max is equal to M max phi max, and L square phi is equal to psi. All these relationship we know. So you put it. L square phi max is what? L square phi max is equal to C Lz square M max. So Lz is M max square and H cross Lz. So Lz phi max is M max. Okay. So using these three relationships, we can expand this L square phi max. This is operating with L square on phi max should give you psi. And I said you that when you operate with L plus and L square on this particular eigenvalue equation with L plus, the eigenvalue doesn't change, it remains same. Okay. So this becomes same. Lz square is this one M max, so it will be M max square, and minus H cross Lz phi max is again M max phi max is equal to 0. Okay. Now so what we can write is C is equal to M max square plus H cross M max square, H cross M max. Okay. And it means similarly you can prove C is equal to M min square minus H cross M min square. And what does it mean? What does it signify? Okay. So if you look at these two relationships, M max plus H cross, both are C. C is equal to M max square plus H cross M max, and C is equal to M min square minus H cross M min. So these two you can equate right hand side. If you equate, what you get is this one. M max square plus H cross M max plus M min minus M min square is equal to 0. This equation is valid only when M max is equal to minus M min or M min minus H cross. This equation is valid only when M max is equal to minus M min or M min minus H cross. If you put these values, you will see you get 0 value. Since M max can't be less than M min, therefore the second option is neglected, and you have M max is equal to minus M min. Okay. So the value of Mk is now M plus minus Kh cross. So if M is M max, M min will be minus K, okay, with a minus sign, where K is equal to 0, 1, 2, 3. So M max minus M min is equal to Kh cross, and 2M max is equal to Kh cross, and for that matter, if M max is equal to half Kh, which you say L, where L is equal to half K and K is equal to 0, plus minus 1, plus minus 2, therefore L is equal to 0, half, 1, 3 by 2, 2, and so on. So this is how the value of L and M are related in quantum mechanics. Okay, this was the equation initially. Okay, so the right hand side of the previous equation is same. Now, if you write 2m min is equal to minus kh, then m min is equal to half kh, and m min will be 0, minus half, minus 1, minus 3 by 2, and minus 2, I think. Minus symbol is missing. Okay. So L square phi is equal to C phi, the eigenvalue independent of k is found to be L into L plus 1 h cross square. This we did earlier also, that when you operate with L square on a function, say any function, psi, and better to write YLM, spherical harmonics, then what you get is L into L plus 1 h cross YLM. This we did earlier also. Okay. So your C is actually L into L plus 1 h cross. In the unit of in the atomic unit h cross we have taken 1. So here C is actually L into L plus 1 h cross. Okay. And so L square phi is equal to C phi, and L into L plus 1 h cross phi, where L is equal to 0, half, 1, 3 by 2, and 2, and so on. Okay. And Lz is equal to mk, which is actually mlh cross or mh cross, where ml is equal to minus L to plus L. So this is how the value of azimuthal quantum number and magnetic quantum number are related, and this we can establish through the principle of angular momentum in quantum chemistry. Okay. The range of eigenvalues of Lz is limited from minus L to plus L, and so the total number of eigenstate possible for Lz is 2L plus 1 state. That we have seen, that if you have this L is equal to 2 value, then I showed you that you have these 5 orientations: plus 2, plus 1, 0, minus 1, and minus 2 orientations. Okay. And this leads to a space quantization of the angular momentum that we talked earlier also. Okay. So but the value is limited by this, by minus L to plus L is proved here, that the m value is limited from minus L to plus L. Okay. And this fact was again known to you. The only thing is that through angular momentum principle we have established it, that there is an upper limit to the values, and that upper limit is actually minus L to plus L for the magnetic quantum number. Okay. Now once we are finished with this one, then exactly in the similar way as we up till now what we have talked about is the orbital angular momentum. Now you are aware of that the electron do have another angular momentum called a spin angular momentum. Electron spin and spin angular momentum. And till now what you have learned is that a spin angular momentum arises because the electron spins around its axis, and so there is a spinning motion of the electron, and this gives you a spin angular momentum, which is totally wrong. There is no counterpart of a spin of the electron in classical mechanics. You cannot say that electron spins like the earth rotates on its axis. Not like that. It's a purely experimental phenomena and observed during an experiment by called Stern-Gerlach experiments. Okay. So exactly in the same fashion as we have designed the orbital angular momentum operators, we will design the same fashion electron spin angular momentum also. Keeping it in mind that there is no classical counterpart for this particular motion, but it is a spinning motion, and this is obtained theoretically when Paul Dirac extended the quantum chemistry to relativistic quantum mechanics. Then he obtained it automatically through mathematics. Okay. So we will not go into those details, but we will exactly copy what we have done for our orbital angular momentum. We will write for the spin angular momentum also. So we say for orbital angular momentum we have written L square YLM is equal to L into L plus 1 h cross square YLM, and Lz is equal to YLM m h cross YLM. So these two relationship is we have written time and again many times for orbital angular momentum. Similarly, if you use a spin quantum number and write the eigenfunction as phi s ms, then you can write s square will give you s into s plus 1 h cross square phi s ms we will write, and for z component of the spin angular momentum, phi s ms is equal to h cross ms phi s. Okay. Now the difference between the orbital angular momentum and spin angular momentum is that for a single electron the value of the s is half, and so the total spin angular momentum root under s into s plus 1 h cross will be root under 3 divided by h cross. Okay. Its z component ms h cross, where ms may have two values plus minus half. So z component of the spin angular momentum will have two components, plus half and minus half. Okay. So two eigenfunctions for single electron you can write. One eigenfunction will be that both spin is positive, and another eigenfunction will be that one of the spin is negative, phi half minus half. Okay. These eigenfunctions are given a symbol alpha. Okay. Alpha for ms is equal to plus half and beta for ms is equal to minus half. Till now we have used theta, phi, y and psi are the eigenfunctions. Now for a spin we write alpha and beta. Okay. Such that if you operate with s square on alpha, the eigenfunction eigenvalue which you get is 3 divided by 4 h cross square alpha. Okay. Because it is s into s plus 1. So s is half plus 1 is 3 by 2, multiplied by 1 by 2 will be 3 by 4. Okay. So 3 by 4 h cross square alpha. Then s square beta is also 3 by 4 h cross beta. If you operate with sz, this is a square of the spin angular momentum. If you operate with sz on alpha, you get half h cross alpha because it is simply mh cross. Okay. So half h cross alpha and sz beta is equal to minus half h cross beta. Okay. So if you represent the sz function, one of the sz angular momentum is this one, another eigenvalue is this one. Only two components, plus half and minus half you get for the sz eigenvalue. Okay. So it's the same principle of orbital angular momentum extended to a spin angular momentum. And now the thing which I said you, that a spin is an intrinsic experimental property of quantum mechanical system. A spin doesn't correspond to any classical phenomena. Why it is not feasible? Let's look at this one. Electron of mass m moving on a circular path of radius r equal to the size of an atom has orbital angular momentum represented in the unit L is equal to mvr, and this we say approximately equal to h cross, h divided by 2 pi. That's why h cross is the atomic unit. Now for this L orbital angular momentum to be equal to h cross, what is required is that the electron velocity should be 1% of the speed of the light. So imagine the kind of orbital angular momentum we are dealing with. We suppose for this orbital angular momentum to be equal to h cross, the velocity of electron should be 1% of the speed of the light. It's extremely fast, but we can physically plausible, physically not impossible. In contrast to this, for a classically a spinning electron, if you suppose s is equal to L is equal to angular momentum to be h equal to h cross, now here L is equal to mvr. So r is very small. We are talking about a spinning motion. So you are taking r is equal to 10 to the minus 15 meter. And for this reason, then the required velocity is 100 times the speed of the light, which is physically not plausible. So saying that electron spins around us exactly as the earth spins on its axis is a joke. We cannot say it, because the kind of spinning motion we are talking about for the electron, okay, if it is a spinning, then the speed of the spinning should be 100 times the speed of the light, which is not feasible. Okay, that's why we say that a spinning motion of electron has no classical counterpart. It is purely quantum mechanical concept, only observed through experiments. Theoretically, it was obtained in the relativistic quantum mechanics by Paul Dirac. Okay. And now commutation relation of a spin angular momentum we can write exactly in the same way as we have written for orbital angular momentum. For orbital angular momentum, you have written Lx Ly is equal to IH cross Lz. So it is Sx Sy is equal to IH cross Sz. Ly Lz was IH cross Sx. So Sy Sz is IH cross Sx. Lz Lx was IH cross Ly. Now it is Sz Sx is IH cross Sy. Again you see the square of the total spin angular momentum and the z component will commute with each other. The same happened in orbital angular momentum also. L square and Lz commute. So we are just copying it. Then another component with the s square Sx, this will also commute. S square with Sy, this will also commute. And we will have a ladder operator in the exactly like orbital angular momentum in the spin or angular momentum also. S plus is Sx plus Isy and S minus is equal to Sx minus Isy. Okay. So if you find out the value of S plus S minus, then you write the two equations. Again you rearrange exactly in the same way as we did, and Sx square plus this will be equal to this one, Sx square plus Y square, and this Sx square plus Sy square will be S square minus Z square plus Hz, and so you can find this value. And similarly you can find this value. The similar equation we obtain in orbital angular momentum also. So we are just using the relationship which we have earlier used for the orbital angular momentum, we are using for the spin angular momentum also. Now electron has two different kinds of spin motions, and so we have orbital angular momentum also and spin angular momentum also. I said that alpha is the eigenfunction. Alpha eigenfunction is with the highest ms value, that is ms is equal to plus half, and beta with the lowest ms value, ms is equal to minus half. You do have two eigenvalues only, plus half and minus half for electron. So when you operate with S plus on alpha, what will you get? Alpha gives you an eigenvalue of ms is equal to half, and this is the highest value. So if you operate with S plus on alpha, it should be 0. And beta is the lowest value, gives you the lowest eigenvalue, it is minus half. So if you try to do further decrease and you operate with a lowering operator S minus on beta, then this also will be 0. Okay. But the reverse, if you operate with S plus on beta, it will raise the value. Okay, because it's the raising operator, and beta is the lower value, so it will go to higher value. Okay, and it will be H cross alpha. Same way, if you operate with S minus on alpha, alpha gives you maximum value, and S minus you are using, so it is a lowering operator, so it will decrease the value, and it will give you H cross beta. Okay, so what do you get? You get a relationship like this one. So all those relationships which you have used in the orbital angular momentum is also used in the spin angular momentum, with the limitation that a spin has only two values, plus half and minus half, and these eigenvalues are represented by eigenfunction alpha and beta. Alpha represents the maximum eigenvalue, plus half, and beta represents the minimum eigenvalue, minus half. Okay, so the operation with the ladder operator is also feasible in case of this spin angular momentum, and operation of the same value also exactly like if you have a Lz is equal to Lz when operated on phi gives you mh cross phi. So same way Sz also we operated on a function alpha or some function y, whatever you want to write, and you get mz. Better write sz h cross y. Okay, similar relationship we are using. Okay, so just this is another motion which is giving you another angular momentum. Now you have two different kinds of angular momentum for electrons. One is orbital angular momentum and another is a spin angular momentum. And if it is moving an electron, Then for a one electron case, what you write is Lz is y Lm. So this equation already we know. For many electron atom, what happens that if you look at the orbital angular momentum only, then this total orbital angular momentum we calculate, and this is given as 0, 1, 2, 3. Okay, and this as a small letter azimuthal quantum number is represented by SPDF, and this is capital letter L, which represents the total orbital angular momentum, is represents each of the value. 0 represents S, 1 represents P, 2 represents D, 3 represents F, and these are called spectroscopic symbols. So we will talk about these spectroscopic symbols for many electron atoms, and we will try to find out the steps there. Okay, but before that, we go for the finding out the term and symbol. We have two motions. One is orbital motion, another is a spin motion, and both these motions will produce a magnetic field, and this magnetic field will interact when placed in an external magnetic field. What will happen if you place a hydrogen atom into the external magnetic field? So it's a rotating charged particle, electron, it will produce a magnetic field. A spinning electron, as conceived here, this will also produce a magnetic field, and both these magnetic dipole orbital, because of the orbital motion and because of the spin motion, these magnetic dipoles will interact with the external magnetic field, and that will result to a change in the potential energy. Okay, that will result into change in the total energy of the system. So the Hamiltonian which we have used here till now in the hydrogen atom is what you have used, minus h cross square divided by 2m del square plus E square by r. E square by r term is an electrostatic term, so in the potential energy. Now we will have to introduce another term for this orbital and spin motion interaction into the Hamiltonian, and that new Hamiltonian will be the proper Hamiltonian for hydrogen atom placed in a magnetic field, and that's why that will lead to a splitting of hydrogen atom spectra, with which you are aware of Zeeman splitting and all those things. So in the next module, I will talk about the Russell-Saunders coupling, or LS coupling we say. How does this coupling takes place? And I will start from the very basic, that how magnetic dipoles are created when you have a spinning or motion of the electron and the orbital motion of the electron. From there, I will take you to the hydrogen atom operators when hydrogen atom is placed in a magnetic field. Okay, so this will be the part of the next module. Okay, thank you.